Isoparametric mapping. Let's talk a little bit about this very, very important concept that we use widely in finite element analysis. Okay. So, let's draw a single finite element. Say we have this is our element, and well, of course we're going to have an axis. Remember that that domain is a part of the reals, right? So this is my E element that is part of our omega h, our discretization. And well, we call this here xi, and that one is xj. Those are the nodes of the element. But what we're going to do now is we're going to say, well, those nodes are actually going to be parametrized by a different variable, and we're going to call that variable c. So if this guy here was x, that other variable is going to be equal to c, and then we're going to have my global coordinate x being parameterized by that local coordinate that is going to go between, let's say, a value here that we say is going to be 1, and then this value here that is going to be +1, right? And we're going to say, well, if this is, let's just call this omega to the purpose of this. This is going to be our omega hat, and the idea is, well, if I have some parametrization of the global coordinate, basically, when dc is equal to -1, I'm going to be at xi, and when it's equal to +1, I'm going to be at xj. That's all there is to it. So then we can write the mapping. Q of c is a function that basically goes from omega hat to omega. So domain codomain notation, just to say that that is basically Q is a mapping that goes from one coordinate to the other coordinate. And well, if we took, for instance, a linear mapping, right, we can write that c as a x as a function of c is equal to 1. This is one function, one shake function, and that is another function. So again, notice that when c is equal to -1, right, this whole thing is equal to 2. 2 divided by 2 is equal to 1. This is equal to xi, because this term goes away, right? 1 minus 1 is equal to 0. And conversely, when I'm on the other side, when c is equal to 1, so 1 minus 1 is equal to 0, so this term vanishes, and then this whole thing here is equal to 1, so I'm an xj. So it's basically a linear mapping between this axis and that axis here. Now, this can be expressed, of course, as the sum of functions I equals 1 to 2 of phi of c multiplied by xi. And you can see now that I'm writing that global coordinate the same way we would write our field. And that is essentially the idea of isoparametric formulations, that you write your field, your displacement field, for instance, the same way you write your geometry. Isoparametric, iso, same, parametric, parametrization, right? The same parametrization is used for both, right? And in HFEM, or the H version of the finite element method, which is what we are going to learn in the first part of this course. Of course, later we're going to go to PFEM. In HFEM, we always work with isoparametric formulations. That means that our geometry is going to be interpolated by shake functions in exactly the same way as our field is interpolated. That is all it means. Yeah?
So the shape functions are the same then, right? Or
the shape functions are the same. the same functions are the same. But notice now that I'm no longer going to define my shape functions as a function of x as we did in the beginning, right? So in the beginning, we were defining our shape functions as a function of the global coordinate, but now the functions are all parameterized on a master element or canonical element. You can find it in some references in this way. So this is going to be the shape function of one node, the one in the left, and this is going to be the shape function of the right node. And all elements, all of them are going to be using these shape functions. Only two. Now I don't have a lot more of shape functions that are defined depending on the value of the node, as we defined it earlier. But now all elements are going to be using only these two functions. Okay? So let's write that down. The same way the field is interpolated. Yeah? And so this means isoparametric. Now, in this particular case, we can actually find an inverse mapping. So we can find C as a function of x, right? And for this particular case, is equal to 2x minus xi minus xj divided by xj minus xi, which is the length of the element. And this is the inverse mapping. Now, this inverse mapping is possible only in this case, that we have a one-dimensional case. And when you go to more more dimensions, when you are in 2D, for instance, there are cases for which the isoparametric formulations, right, are a bit more tricky, because sometimes you cannot find an inverse mapping so straightforwardly, right? Like, for instance, triangles in 2D have an inverse mapping, but quadrangular elements no longer have a very straightforward inverse mapping, and so you need to solve a nonlinear equation to get to the inverse mapping. So in other words, finding the z coordinate in the master element, right, given a global coordinate, sometimes it's very straightforward, like here, but sometimes it's a little bit more difficult. Okay? Okay, so why do we use this? Well, the idea is that now that we are basing our functions on one master element, well, now this can simply be used for integration, because, well, all our integration rules are defined on this canonical element. And then we can do numerical quadrature of these functions. And that is actually the main purpose of doing this. Now, we can do all integrations on an element for which we have predefined set integration rules. All these Gaussian quadrature rules are defined on this master element. So we use mainly this idea of isoparametric formulations for integration. And so if we have, for instance, if we express an integral xi, xj of some function that we call f of x dx, then now we are going to express that integral as, well, of course, we have to change our domains of integration. So the integral is going to go now from -1 to 1, right? F of x still like this, but now we have j dx, and j is a so-called Jacobian. This guy here is our Jacobian. And in essence, what that Jacobian physically represents is the relationship between the lengths of the two different elements, right? So if in physical space, right, we have, I don't know, an element of size 4, right? And then my canonical element has size what? 2. Thank you, sir. Yeah, so now that ratio is basically represented by the Jacobian. So it's a relationship between lengths. And you can already understand that whenever we're going to move to higher dimensions, if we are going to 2D, for instance, and I have two triangles, right, that Jacobian is still going to be representing something similar. So in a two-dimensional setting, right, we're going to have the ratio between what? Areas. And in 3D, volumes. So that is a physical representation of that Jacobian. Okay? Now, yeah.
Isn't it f eta?
fxc? No, it's still f of x. It's still, we're integrating still that function. And we're going to see with an example of the stiffness matrix, because in that stiffness matrix, remember that we are going to be using these functions. Now, functions of c. So there is a little subtlety there, because of course what we want is actually something that is related to the global coordinates. And in the stiffness matrix, this becomes very clear because we have derivatives of the shape functions with respect to global coordinates, right? But so how do we do that? Because we no longer have the shape functions in global coordinates. We have them in local coordinates, right? In master coordinates. And so there has to be a change rule there that we have to apply to get to our final version of our integrals, okay? And we will look into this. So, okay, but we're not done, because now that we have changed the domain of integration and the Jacobian pops into the integral, that is going to be represented as the sum of I is equal to 1 to the number of Gauss points. Remember, now we have quadrature points, right? Where we evaluate our function at those quadrature points, right? And then we have the weights that are associated with those quadrature points multiplied by, again, the Jacobian. Now notice that I wrote here xj, right? But it is actually xi as a function of ci, because this is actually the quadrature point, right? And so that basically means that given a quadrature point in master coordinates, well, we're going to have to find what would be the global coordinate, right? So that I can evaluate this function. So this is very important. This is not a function of c, this is a function of x. And therefore, given a quadrature point c, I'm going to try to find first x so that I can evaluate that function and then integrate. Yeah, you have a question?
What is that letter next to fx?
This is gamma I, right? And it's the weight that is associated to the quadrature point. Okay. Now, well, I could have used w, but we use w for the test function, and so I had to find a different symbol, right? So I use this gamma to denote that the weight that is associated to the Gaussian rule, okay? Now, notice also that this integration may not be exact, and so I'm going to just write an approximation here. It is going to be exact in some cases. Anyone has an idea? Which cases? Well, yes, a quadratic polynomial you can integrate exactly. What else? Any polynomial, basically. So all these quadrature rules are defined in a way so that you can integrate polynomials exactly, and in those cases, that is going to be the exact integral. In other cases, there may be an error. You have a question?
This is localized, right? Because I see that the Jacobian is a small case.
Yeah, well, I reserve the uppercase J for the Jacobian matrix. So this is a scalar, and as we discussed, is the ratio between the lengths of the physical element to the local element. But let me finalize this expression, and I'm going to write here, since dx is equal to xj minus xi, which is the length of the element, c divided by 2, and that is simply just basically applying the derivative of x. Then again, this here, xj minus xi is the length of the element, so I'm going to write that as le divided by 2 dxc, and so that is what I call j, right? Is the length of the element divided by 2, going back to, okay, the ratio of those two lengths. Okay, but let's apply this to a concrete case, and a concrete case is our stiffness matrix for the element. Okay, so now we said we're going to have if you remember, the expression was our lowercase ke it was the integral between xi and xj, and then we have ea d phi dx transpose d phi dx. Notice that these are functions, basically the shape functions are the derivatives of the shape function with respect to global coordinates. And so now that I'm going to make the transformation into our canonical element, this is going to be the integral between -1 and 1. And then I have ea d phi transpose dx, sorry, dxc dx, and then I have the same d phi dxc dx multiply times j multiply by dxc, right? And now notice that this expression here, dxc dx, is what? What is that? So this guy here, what is it?
Is the b. No, is the b, but like in the other coordinates.
So now remember that b is this whole thing here is b, right? The derivative of the shape function with respect to global coordinates, that is what we define as our strain displacement matrix. But now we said we no longer have our shape functions as a function of global coordinates, but as a function of local coordinates, and that is why we have this change rule. But I want to ask you, what is this guy here? What is that?
Oh, we see it already. It's one. Or
It's a half. Right?
Yeah, thank you so much. It's the inverse of the Jacobian, right? If dx dxc is equal to j, right, then dxc dx is 1 over the Jacobian. And so this whole thing is going to be equal, or let's say now that we're going to evaluate in this expression at fixed locations that we call quadrature points, that is going to be equal to a sum I equals to 1 to the number of Gauss points. And then I have this whole expression in. So this guy, right, d phi transpose d c, d phi dc, and then I have 2 divided by the length of the element. All of that, all of it, evaluated at the location of the integration point and multiply by this guy. So again, that is because these guys here are basically 1 over j. And j is the length of the element, right? And so we have 1 over j squared multiplied by j, and now we have, of course, that is popping up here. All right? So this is essentially the way we do the integration of our local stiffness matrix. And we do it like this. Normally, in standard finite elements, we do it like this. Given whatever expression you have, right? Let's say I don't know, inside your element, your Young's modulus is going to be changing, or your area is going to be changing, right? We pick locations where we are performing these evaluations numerically, and then we are adding that up. And that is the basis of the code that I'm going to share with you, or it's already shared with you in the Brightspace, right? So we do numerical quadrature. We evaluate all these integrals by summing up the contributions of each one of these integration points. And of course, if you do that, in this particular case, if you notice the shape functions that we're using, right? So these here are our shape functions. Well, those are linear, right? So the derivatives of that are very, very straightforward, right? And so if you plug that in, for this particular case, again, for this particular case, then our stiffness matrix is going to be approximately equal to EA divided by L. Actually, for this particular case is actually equal, right? Because we don't have the problem like EA is going to be constant, so we're still integrating polynomials. So for this particular case, it's equal, right? So we have, sorry, this is LE. Then we have our famous matrix 1 minus 1 minus 1, 1 for piecewise linear polynomials. As I said, for this case and this case only, right, this is the case we get exact integration because we can integrate polynomials exactly, right? Every time that we're doing numerical quadrature on polynomials, we can integrate them exactly. And there is this rule that in 1D, n integration points integrate exactly, right, a polynomial of degree 2n minus 1 equal to p. That's a polynomial order. Yeah, so for instance, if I want a linear, if I have a linear polynomial, then how many Gauss points I need to integrate a linear polynomial? 1 point. 1. If I plug here 1, then I have 2 minus 1, 1. If I have a cubic polynomial, how many points I need? 5 is too many. So if I put 3 here, 3 times 2, 6 minus 1, 5. So it's not 3. 2, right? 2 times 2, 4 minus 1, 3. So a cubic polynomial is exactly integrated with 2 polynomials. And this is what I want you also to experiment with. So in the project, right, in the first exercise of the project, I give you a function that you're going to have to integrate. It is not a polynomial function, right? It is a rational function, right? A rational function cannot be integrated exactly. So then you start wondering, well, so how many Gauss points I use, right? Well, since you know that you're not going to be able to integrate exactly, one of the tasks in the project is, okay, you have to think how I'm going to be integrating this function so that it makes sense for the purpose of the project, right? And you're going to develop your own strategy, right? What am I going to do to integrate this term here that is a force vector so that it makes sense for the purpose of my project? Because it's not going to be able to be integrated exactly with numerical quadrature, okay? Any questions related to isoparametric formulations? Yeah?
Can you re-explain from the inverse Jacobian, how do you lead to 2 over LE?
What part? This part?
Yeah, from this part to the bottom part. Yeah.
Well, so you see it here. So this guy, CDX, is 1 over j. So here you have this. It's basically twice. So you have 1 over j squared. And then that is multiplied by j. So in the end, all that cancels, and then you have 1 over j. And that is why this 2 over LE shows up there, right? That is inverted as opposed to just the Jacobian LE over 2. Yeah? So let me tell you a couple of more things about this isoparametric formulation. So of course, we're dealing with linear fam, right? This is very simple. When we go to high order approximations, it is not going to be this simple, right? Because you could argue, well, say we're using, we're going to PFAM, and now my field can have any arbitrary polynomial interpolation order. Say I want to use a kinetic polynomial to represent the field. Now, would it make sense to represent the geometry with a kinetic order polynomial in 1D? It makes no sense, right? So what will you choose? Linear. So we keep a linear approximation for the geometry. Really, it does not make any sense that in a kinetic setting where my field is approximated as a kinetic polynomial, right, that I make this geometry mapping a kinetic polynomial. So I want to keep the linear interpolation so that, okay, so this node goes to that node and this node goes to that node. That is basically the idea. And that is no longer an isoparametric formulation. We call that subparametric, okay? In the sense that now my geometry is interpolated with a lower interpolation order, right? There are cases also where our geometry is always interpolated exactly, always. Like for instance, if you grab a CAD model, right? Now you have these NURBS, non-uniform rational splines, right? In those cases, your geometry is always going to be exact. But you could argue, well, I'm going to use shake functions for the field that are a quartic polynomial, but your geometry is still exact. Those formulations are called, so if these ones are isoparametric and a lower interpolation for geometric is subparametric, a high order interpolation for the geometry is called superparametric, right? And superparametric formulations are not very common, especially because they have issues. We did a study. We said, okay, let's grab this formulation that we developed for fracture, and now we are going to basically try to use NURBS to represent the geometry exactly, and then we kept our field linear. That's a superparametric formulation, right? Where geometry is exact and our field was linear. Well, that led to so many issues. We had artificial states of stress in the domain that were just numerical artifacts. So you cannot reproduce a rigid body most with superparametric formulations. So they are not used at all. Okay. Okay. So as I said, this was going to be a very quick lecture on isoparametric formulation. This is very, very important because in the end, this is the way we do crunching, number crunching in a computer with this type of formulations. Okay. So I'll see you guys next Tuesday. And of course, as usual, I will be posting the lectures online today.